Here, let's take a look at a sample problem. So it says a rectangular block of iron has dimension of this one 1.2 times 1.2 times 15 centimeter cube. A potential difference is to be applied to the block between parallel sides in such a way that those ideas are equipotential surface. What is the resistance of the block if you have two parallel sides? One, the square ends with dimension 1.2 times 1.2 centimeter square, and two rectangular sides with with dimensions 1.2 times 15 centimeter square. Okay, so for the first case, it is like this is 1.2 times 1.2 and then times 15, like this, like this. Okay, for the second case, it is like 1.2 times 15. 1.2 times 15. Okay, and then times 1.2. Okay, we try to use that one like this. Okay, so this is a two different case. So in that case, L and A are different. Okay, for the first case, okay, the cross-section area is this one. Okay, so the cross-section area A is 0.012 quantity square. So it is 1.44 times 10 to minus 4 meter square. So in that case, we can use R equals rho times L over A. Okay, so this is L, this is A, this is A, this is L. So this one, rho is this value, 9.86 times 10 to the negative 8th power, times L is 15 centimeter, which is 0.15 over 1.44 times 10 to the negative 4th power. So this number is 100 times 10 to the negative 6 ohm, or 100 micro ohm. Okay, which is quite small, but at least it will be larger than the next one. You can imagine, this is longer and the cross-section area is smaller, so the resistance is larger. For this one, the cross-section area is much larger and the length is much shorter, so this one should be much shorter, the resistance should be smaller. Okay, for the second one, A is actually that one, 0.012 times 0.15. Okay, don't need the parenthesis. Okay, so this is actually 1.8 times 10 to negative 3rd power meter square. Okay, so you can see at least one order larger cross-section area. So R will be rho times L over A. Okay, rho is the same, 9.86 times 10 to negative 8th power. So times, this is L. L is 0.012, and then over 1.8 times 10 to negative 3rd power. Okay, so this is 0.65 micro ohm. Okay, so much smaller. Okay, so this is 0.65, this is 100. They have the same prefix, micro ohm. So this example is quite easy to somehow try to use this equation. Okay, so next is the Ohm's Law. Ohm's Law is very trivial. So it is nothing but V equals IR, so I don't try to mention too much. So which means that, okay, I try to mention a bit about that. So this is a resistor. Usually in the circuit diagram, we will draw it like this for a resistor. Denote it as R. Okay, like this. And then if the current I is from left to right, the potential difference or the voltage difference should be this one, this side higher, this side lower. I usually will denote it as V, and then with a plus sign on one of the node and then negatives on the negative node, which means that the electric potential of this point subtracting the electric potential at this point will be V. Okay, denote it like this. Okay, so I is from positive to negative. Okay, so hope you can remember this relationship. Okay, it is only V equals IR, but actually there are some direction. Actually, not the direction of the vector. They are not vector either, but you need to be careful about the direction. So the direction of the current. Well, even though current is not a vector, it has a direction. Okay, for the voltage, you need to know which side is higher, which side is lower. So if if the current is from left to right, this side is higher, this side is lower. If the current is from right to left, the right side is higher, the left side is lower. Okay, so V equals IR is nothing special, it's just a line, Y equals MX, something like that, even without the plus D. Okay, so this is V equals IR, it's just a straight line for some of the material, like the conductor, like the insulator, but not for the semiconductor circuit. Okay, this is one of the semiconductor circuit. So it says figure C is a port of another conducting device. Current can exist in this device only when polarity V is positive. Yeah, the applied potential difference is more than about 1.5 volt. Okay, so here. Okay, when the current does exist, the relationship between IV is not linear. Okay, this is not linear. This is linear, like a straight line. Okay, it depends on the value of the applied potential difference V. Okay, any one of you know what is the device it is describing? Any of you know that? Maybe you know the Chinese name. Any one of you know that? Okay. No, none of you know that. Okay, this is actually the characteristic of a diode. Diode. Okay, in Chinese name it is called 二极体. 二极体不是两极. 二极体. 二极体. Okay. 二极体. The circuit symbol will be like that, but actually you will not use it for. I don't think you will use it for this course. Okay. Anyway, for an even similar circuit model, it will be like something like this. It will be something like this. Okay. If it is forward bias, which means that if this is the positive side, this is the negative side. If you provide a higher potential there, then there will be current, and there will be no potential difference between the positive and negative. No. If you provide a lower potential there, then there will be no current going through. Okay, it will be like that. Yeah, so here Ohm's law, I is proportional to V, I equals V over R. Okay. So this is a quick checkpoint. It asks you which device 1 or device 2, which of them does not follow Ohm's law? Which of them does not follow Ohm's law? Okay, so you can see V is 2, 3, 4. I is 4.5, 6.7, 5, 9, and then this is V is saying 2, 3, 4. I is 1, 2.2, 2.8. Which one does not follow the Ohm's law? Yeah, quick. You can quickly see that it should be this one. Okay, you can see this is 2, this is 4, this is 4.5, this is 9. Okay, so they are in the same ratio. Okay, but this one 2 to 4, 1.5 to 2.8. So this is device 2. Okay, so next we talk about the Ohm's law in a microscopic view, or something like the hardcore physics stuff. Actually, this equation does not really correct. But this is really important. This is important because the physician tried to get the Ohm's law using some measurement. It is something like the correlation, 相关性. Okay, which means that if we try to change the current or change the voltage, change the voltage, and then you measure the current. Okay, and then you find that the V and I follow a straight line. Okay, then they try to summarize it. Oh, okay, if I try to use a line to fit the measurement data, then it is the V equals IR. But it lacks of some physics nature. Okay， 没有一些物理的一些理论在里面。Okay, so it tried to use some microscopic view to derive something which can verify or the Ohm's law can be correct. Okay, it doesn't necessarily that they give you the same result, but it tells you that the Ohm's law will make sense. Okay. So here, let's see how it will try to interpret the hardcore physics. So it says, assume the conduction electron in a metal are free to move. Okay, like molecules in a gas leads to expression for resistivity of a metal. Of course, it makes quite a lot of assumption, not necessarily completely correct. So yeah, so but at least it can give you some interesting conclusion. Okay, so if an electron of mass m is placed in an electric field of magnitude E, the electron will experience an acceleration. Okay, so this is actually so if you place an electron in the E field, then it will move. Okay, this is what we have learned in chapter 22. So so this is the E field. Okay, then the F should be if it is a positive charge, then the force follows the direction of the E. If it is a negative charge, it is opposite to the direction of E. Okay, so never mind. Okay, so here we don't really consider whether it is a positive charge or negative charge yet. Okay, so but actually, as much as they are force acting on say an electron, then there will be a force, and then there will be acceleration due to the Newton's second law of motion. Okay, F equals ma. So F is actually E times E, or Q times E. Q is E, which is the electron. Okay, so we have F equals EE over m. F equals EE. So A equals EE over m. And then here we try to assume that the drift velocity, the drift speed is Vd equals A times tau. A times tau. Okay, so this is A. This is A. And then the tau means the average time between collisions. The average time between collisions, which means that suppose I have an electron here. Okay, so it may try to accelerate from 0 to maximum speed, and then it might collide something. After it collides something, it will turn to another direction and then go and then accelerate again, and then collide with another things, and then it try to turn to another direction. Okay, and then up to here and there and then there. Okay, so the electron is like at the beginning it is stopped, and then it try to accelerate and then collide and then turn around and then accelerate again and then collide, so on and so forth. Okay, so so this is tau is like the average time between collision. Okay, so we use this one. This is a time for the electron to accelerate. Multiplied by the acceleration will be the speed. Okay. Someone may ask, whether you should multiply by 1/2. It is not that important because finally the equation doesn't necessarily give you a very accurate value. So this 1/2 factor is not that important. Okay, so and also suppose we already consider this is the average time, so we don't need to consider the average value either. So this is like Vd equals A times tau. Okay, so next we can try to plug in A to here. So we have EE over m times tau. Okay, this is Vd. And then previously we also have J equals NEVD. Okay, so we can plug this one into here. So we have NE times EE over M and then times tau. Okay, so we plug this one here. We plug this one here. Okay, so next we try to rearrange the term. Okay, we only keep E on the right side and we move all the other terms over. So on the left, and then so we have E to here and then J on the right side. And then all other terms move to this side. So we have NE square, NE square, NE square here, and then also tau in the numerator, so it moved to the bottom. And then M move to the top. Okay, so from this one we can get this one by rearrange the terms. Okay, so and also we have this assumption. We have also this assumption E equals rho J, which is the vector version of the Ohm's law. Okay, so comparing this one and this one, we have E, we have J and J. So this one should be the same as this one. So we have rho equals M over E square and tau. Okay, like this. And we already mentioned that rho is a constant for a given material. And here we can see that M, so we can verify that like M is the mass of an electron, it should be a constant. E is the elementary charge, it should also be a constant. And then for the N is the electron density. Okay, so for a given material it's also constant. And then for the average time between collision, so it relates to the shape, related to the material also. Because for different material the distance between atoms will be different, but for given material the distance between atom and atom should be similar. Okay, so we will also assume that given a material, this tau is also a constant. So which means that given material, this is a constant. So this verify why this is correct. Okay, this should be a constant. So given a material, the rho should be a constant. But of course, it is related to the absolute temperature as I mentioned. Okay, so if you increase the temperature, it might influence the distance maybe. So it will change the tau. Okay, so it will change the rho. So but if you just make the temperature, the absolute temperature to be constant, then this derivation which means that the Ohm's law in a microscopic view verify the Ohm's law in the macroscopic view. Okay, and or actually is like V equals IR. Okay, so we know that we can use V equals IR to derive this thing, or the vice versa. So these two are actually the same thing. So so if this derivation verify this one, it also verify this one. Okay, so here it also mentioned that rho equals to this value. Okay, nothing special. So here let's take a look at another sample problem. So it says, what is the mean free time tau between collision for the conduction electron in copper? Okay, so this is easy. We only need to use the formula we just derived. Tau equals M over NE square rho. Okay, and actually we can have all the variable N rho from the table 26.1, and then mass of electron. Okay, mass of electron 9.11 times 10 to negative 31, and then N is 8.49 times 10 to 28th power, and then times 1.6 times 10 to minus 19 quantity square, and then times rho is this one, 1.69 times 10 to negative 8. Okay, so this is nothing special. 2.5 times 10 to negative 14 second. Okay, if you would like to express it as scientific physics, this is 25 femtosecond, which is really short time. Okay, if you just take the reciprocal, it is like, yeah, it is like 40 terahertz, not TG, T terahertz. Oh, take the reciprocal, 1/25 femtosecond. So it is like 40 terahertz. You know gigahertz for the device, for the CPU, for the GPU or whatever. T is 1000 times larger. Okay, so this is tau. Okay, so the mean free path lambda of the conduction electron in a conductor is the average distance traveled by an electron between the collision. So what is lambda for the collision electron in copper? Assuming that their effective speed, V effective, is this one. Okay, so it is just like S equals Vt. So lambda equals V effective times tau. Okay, so we try to estimate how long does it take to collide. So this is the time it takes to collide. What is the length it takes to collide? So 1.6 times 10 to the 6th power. So for this sample problem, the calculation is really easy. But based on this number, it tries to let you know some physics stuff. So 25 times 10 to minus 15. Okay, so this one is 14 nanometer. Okay, not that small. Okay, so this is 14 times 10 to negative 9 meter. Okay, looks very small, but yeah, not that small compared with the atom. Okay, so it says this is about 150 times the distance between nearest neighbor atoms in copper lattice. Lattice is Jinge. Maybe you have heard this term in high school chemistry. So this is about 150 times, which means that for the lattice, I'm not sure whether it is like a rectangle shape. So yeah, if it is like this, okay, this is a Cooper. So it takes 150 times. So maybe an electron start from here, and then it goes through 150, and then it collides with another nucleus of the Cooper. So this one somehow tells you that the copper or the conductor is not really a very dense. It should be like a nucleus is there. And then with quite a lot of space in between, so that the electron can be able to go through. Otherwise, if it is really dense, if the atom is like this, then the electron has no way to go through so much distance until it collides. Okay, it tells you that there should be quite sparse, 很稀疏的. Thus, on average, each conduction electron pass many copper atoms before finally hitting one. Okay, so it tells you some physics. Okay, so here, yeah, power. We talk about power. So for power, so the derivation is like du, which means a small change for the potential energy is dqv. Okay, if you still remember, U equals qv, and then q. Okay, so here we would make v to be a constant. So we have dq, and if you still remember, I equals dq dt. Okay, I equals dq dt. So dq equals I times dt. So we have iv dt. And then we try to integrate on both sides. integrate on both sides. So this is power. Integrate the power over time will be the power. So for this case, integrating this will be dt. Okay, so it will be I times v. Will be I times v. Will be I times v. Okay, or actually you, no, sorry, it is not it's not integrating on both sides. Sorry, it should be like you move dt to the left side. Okay, yeah. So if you move dt to the left side, so it becomes du over dt. Du over dt is the power, and then it is I times v. Okay, so we have P equals I times v. Okay, so if we have a v to be like this, and then you know the I, then I times v will be the power consumed by this conductor or this resistor. Okay, for the resistor it will be correct. Actually, for any, even for semiconductor, P equals IV is correct. But yeah, if you make it like this one should be I square R. This one should be I square R rather than I square V. Okay. Okay, if you have an I square R, V square over R, they are correct for resistor, but not for other device, but not for like a semiconductor circuit. Okay. Only P equals IV is uniformly correct because we try to derive it without considering whether this is a resistor, and then we come up with P equals IV. So this is correct for all the electron device, but this one only suited for the resistor. Okay, P equals I square R, P equals V square over R. You only need to plug in V equals IR equals V. Plug in here and there, then you try to eliminate V, eliminate I, and then you will get these two. It is easy algebraic calculation. Okay, here for the semiconductor. Yeah, we talk about the semiconductor and superconductor. Actually, I just mentioned semiconductor in the last hour, but yeah, actually it tells you that more charge carrier available decrease the resistivity. Yeah. So just like what I've mentioned, yeah, for the pure semiconductor, the resistivity is high, which means that the conductivity is low. Okay, and then we need to add some, yeah, so yeah, increase very rapidly, makes more charge carrier available. Okay, so another thing is like, try to increase the temperature to make the charge carrier available. But actually for the semiconductor circuit, we try to add some 5A element or 3A elements into it to make it like P-type, N-type semiconductor, so on and so forth. Yeah, so I don't want to talk about more because it is really difficult. It takes several semesters to talk about the semiconductor device. Okay, so here we try to also simply introduce the semiconductor, 超导体. So it is very interesting. So superconductors are material that lose all electrical resistance below some critical temperature. Okay, just now we mentioned that the resistivity is proportional to the absolute temperature, like this page. Okay, just now we mentioned this one. Okay, I just now I'm already also mentioned that I'll talk about the exceptional case here. Okay, when we try to zoom in this part, then it is actually this one. Actually, the physician would hope that this would be something like a straight line or until it goes to zero. But actually, the case is not like that. The case is like it suddenly dropped down. They think whether this is an experimental error because this temperature is really low, 4K, 4K or 3K. 4K is like negative 269 degrees Celsius. Okay, you can imagine how cold it is. Yeah, so actually, at that time, the physician has the liquid helium, 液态氦, 液态氦, so that they can, and then they try to manipulate the pressure. So you know the PV equals nRT in the high school chemistry class. So you know if you try to manipulate the pressure, then you will be able to change the absolute temperature. Yeah. So yeah, with the liquid helium, with some pressure manipulation, then they can create an extremely a low temperature environment to test the circuit. Okay, and then they find, oh, this is really strange. If it goes to, this is roughly 4 absolute 4K 4 Kelvin, the resistance suddenly drop down to nearly zero, to zero. Okay, so and later on we call this thing the superconductor, because it does not have any resistance, which means they don't have any loss. Here it tells you that if we have resistance, we will have power loss. It will consume the energy. But if it doesn't have any resistance, then it doesn't consume energy at all. So most such material require very low temperature, but some become superconducting at temperature as high as room temperature. So the scientists try to find some material which can have superconductor effect higher and higher. And yeah, for some of them, maybe for the quantum computing, 量子计算, they also require this kind of superconducting effect, so that the electron can be under control. Yeah, for some of them, they would like to trap an electron at a specific position, and then they try to make it to do some computation. Then they need to make it at a very low temperature. One of my high school classmates doing the quantum computing in Hong Kong. So he has told me that they need something like 500 mK, 0.5 K, as low temperatures as that to make the so-called the quantum entanglement, something like that. Okay, yeah. Okay, so that is all the content for this chapter, and we have some additional example here. So let me try to do that. So for this one, the first one, the figure shows a person and a cow, each a radial distance d from the point where the lighting. Okay, so this is a lighting hitting this point. Okay, so the current I is 100 kA kilo ampere strike the ground. So the current spread through the ground uniformly over a hemisphere, 就是半球形. Okay, so it's spread out in different direction. Okay, so center on the strike point, the person's feet are separated by radial distance, like this, delta R pearl. Okay, so 0.5 meter. Okay, and then the cow front and rear hoofs. Okay, 前后脚. Okay, so are separated by radial distance, delta cow 1.5 meter. The resistivity of the ground is rho. Ground is this one, and the resistance for both across the person between the left and right feet and across the cow between the front and rear hoof is out to be 4K ohm. Okay, so which means that this is a resistance. Okay, 4K ohm. Okay, so this is also a resistance 4k ohm. Okay, and the current try to goes from here and then going through here. Okay, so also the current going from here to here. Okay, so you may feel like this is a little bit painful. Okay, so we try to calculate what is the current I pearl through the person. Okay, what is the current, okay, going through. Yeah, so so E is rho ground J. Okay, we try to get this E equals rho J, and then J, we will assume that J is uniform. So this is like rho equals I over 4 pi r squared. 4 pi r squared. So actually the I here is from the lightning, okay, hitting this point, and then they spread it through different direction. Of course, in a 3D, it's a hemisphere, it's a bunch of, okay, so it goes through different direction. So yeah, so this J only consider, so the cross section area is like this is a smaller hemisphere, larger one until this one. Okay, so sorry, this should be 2 pi r squared because it's only a hemisphere rather than 4 pi r squared. Okay, so we will consider this is the cross section area. Okay, and you can also see that J is not uniform for the whole path. Then we will need to do the integration. Okay, so in that case, this is it. And then we would like to consider the delta V. The delta V from here to from the left foot to the right foot. Okay, so delta V should be negative integration of E dot times dr. Okay, we just ignore the direction because we will consider E and R are parallel to each other. And then actually we need to integrate from this is 0, this is D, this is D plus delta R, D. So we integrate from D to D plus delta R. Of course, there is a delta R pearl and delta R cow. So we just make it delta R first, and then if we substitute 0.5, it is for the person, and if we substitute 1.5, it is for the cow. Okay, then we can plug in this term into here. So we have negative integration of rho I over 2 pi. Sorry, it should be small r. Small r squared. Okay, small r squared dr. Like this. Rho ground. Forgot. Rho ground. Okay, so most of the terms are constant, so we can just put it out. So rho I over 2 pi. I mean rho ground. Rho ground I. Okay, over 2 pi. And then we integrate from D to D plus delta R. Integrate from D to D plus delta R. And then we have dr over r squared, like this. Okay, so for the integration, this is r to the negative second power. Okay, so for the integration, the antiderivative is the order plus 1. So negative 2 plus 1 is negative 1. So it is negative 1. And then for the chain rule, you also need to divide by negative 1. So that this negative 1 will cancel with this negative sign. So it becomes rho ground I over 2 pi and then times 1 over r, evaluate from D to D plus delta R. So it turns out to be rho ground I over 2 pi, and then we have 1 over d plus delta r minus d. Okay, this is roughly the expression, but yeah, somehow we can just simplify it as negative rho ground I over 2 pi, and then for the denominator it is d times d plus delta r, and then here we have this one minus this one, we have a negative sign, and then with delta r in the numerator. So for the R pearl, we just need to plug in the corresponding number. So rho ground is 100 ohm meter. So this is 100. And here we only consider, I mean it should be delta V over R, delta V over R, then it is okay. So delta V will be, so we just ignore the minus sign. Okay, it is 100 times I is this one, 100 times 10 to the third power, and then times delta R pearl is 0.5 over 2 pi is 2 pi, and then times D is 60 meter, and then this is 60 plus 0.5. Okay, so this is delta V, and then don't forget the R is 4K, 4 times 10 to the third power. Okay, so this number is 0.05488. Okay. Okay, so there will be this amount of current going through the person. And then for part B, we don't need to derive the whole thing again, because everything will be the same, except delta R, we should use delta cow. Okay, so we just change 0.5 to be 1.5. So I cow is nothing but 100 times 10 to the third power over 2 pi, and then times 1.5, and then here 60 times 60 plus 1.5, and then times 1 over 4 times 10 to the third power. Okay, so all the way the same, but except this one and this one. Okay, so this is 0.1628. 0.1628. So I cow is roughly 3 times larger than that. 3 times larger than that. Because the distance here is larger. Okay, the distance here is smaller. So this somehow tells you that when there are lightning, don't try to split your leg. Don't try to split your leg, and the current go through. So you should try to stand straight. Okay, so this is the second one. So what is the current in the wire of radius r in the magnitude of current density given by this one, in which r is the radial distance and J0 is this value? Okay, so here we try to have a example to get familiar with the integration. So IA, so this is for question A, so I put the subscript A here. So integration of JA dA. Okay, so we can just plug in this one. JA is J0 R over R, or R over capital R. dA should be the one for the polar coordinate. So it is R dr d theta. Oh, I do not repeat it again. So here we consider the whole circle. So we integrate from 0 to capital R. And then for the theta, it's from 0 to 2 pi. Okay, so we just move J0 and capital R out. Okay, it's J0 over capital R. And then we have R squared dr from 0 to capital R. And then integrating d theta from 0 to 2 pi. Okay, so in this case, this is R cubed over 3. This is 2 pi. So this is J0 R squared over 3 times 2 pi. Or you can rewrite it as 2J0 R squared pi over 3. Something like this. Should I... yeah, actually I need to plug in the number. So this is 2 times J0. J0 is this one. 5.5 times 10 to the 4th power. And then R squared is 3.4 times 10 to negative 3rd square. And then pi over 3. So this value is 1.338. 1.338. Okay. Okay, so for part B, it changed the current density JB to be J0 times parenthesis 1 minus R over capital R. Okay, all the other things are the same. Okay, so here we have IB equals integration of JB dA. So it will be integration, and then we have a J0 1 minus R over capital R. And then R dr d theta, and then integrate dr from 0 to capital R, and then d theta from 0 to 2 pi. Okay, so we can just move J0 outside, and then here we have dr. Okay, we cannot separate, so we need to keep it there. So we try to distribute R here and here. So we have R minus R squared over capital R, like this. Integrate from 0 to R. And then we have an integration of d theta from 0 to 2 pi as usual. So this is the same thing, 2 pi. For this one, this is R squared over 2, R squared over 2, minus. This one will be R cubed over 3, R cubed over 3, and then over R will be R squared over 3. Okay, so for this thing, it will be R squared over 6. Okay. So this is, let me see, this 2 and this 6 can be cancelled partially. So it becomes pi J0 R squared over 3. Okay, so pi is pi, and then times J0 is 5.5 times 10 to the 4th power, and then times 3.4 times 10 to negative 3rd power quantity square over 3. Okay, so this value is 0.6678 for the part B. Okay, so for the part B, it also asks you what is the current, and then here we have part C. It asks you which function maximizes the current density near the wire surface. Maximize it. Okay, so you can just have a simple observation is okay. For part C, you can observe that JA equals J0 times R over R, and then JB equals J0, and then 1 minus R over capital R. So it asks you current density near the wire surface, which means that R is capital R. R is capital R. JA is J0. J0 times capital R over capital R. So capital R cancels. And then for JB, if R equals capital R, so this is 1, 1 minus 1 is 0, so this is 0. So which means that this one maximizes the current density, so JA. Okay, let me finish this one quickly. So it asks you what is the Y section. So we have a section 1, section 2. This one has a larger radius, this one has a smaller radius. And then there is a current going through. Okay, so this says the curve has a current. Assume that the current is uniform distributed across any cross-section area through the wire's width. Okay, so we have potential V along the length L, 2 meters, shown in the section 2. Okay, so this is V to be 10 microvolt. Okay, the number of charge carried per blah blah blah. This is the charge density. The charge density. So what is the drift speed of the conduction electron in section 1? So it asks you VD here. Okay, so here we try to get E2 equals V over L. Okay, so assuming E is uniform. Okay, so V is 10 mil over 2, so which is 5 mil V over meter per meter. Okay, so this is E2 in this region. And then we make use of the Ohm's Law, the vector form of the Ohm's Law. So E equals rho J. So J equals E2 over rho. E2 over rho. So this is 5 mil over, this is rho, 1.6 times 10 to negative 8. So this is 296 A per meter squared. So we get J2. So we should have a I to be the same thing. So we have a J1A1 equals J2A2. Okay, equals to the same I. Okay, but actually we would want to find J1 to be J2 times A1 over A2 over A1. A2 over A1, and then we can just plug in the number 296, and then we know that D1 is 4R, D2 is 2R, which means that this is like pi R square. Okay, so the R is 2, R1 is 2R, and then R2 is R. Okay, so you can get a pi R1 square, pi R2 square. So this is 4 times. So this is a pi R square, and then 4 pi R square. Okay, so J1 will be 74 A per meter square. Okay, smaller than that one because the cross-section area is larger. This is the cross-section area. The cross-section area A1 is larger, A2 is smaller. Okay. Okay, so this is D1, this is R1, this is R2. Okay, so finally we can find VD to be J1 over NE. So J1 is 74 over N is this number, 8.49 times 10 to the 28th power, and then times 1.6 times 10 to minus 19. Okay, so this is 5.44 times 10 to negative 9 meter per second, even slower than the one we got in the previous example. So this is 10 to negative 9 nanometer per second. Okay, so we have finished off this